Okay guys, so this was the last of the notes from last time. We have the cumulative frequency and the relative cumulative frequency. And now we're going to talk about an ogive. You don't actually have to copy this whole chart down if you don't want. You could print off just a screenshot of this or freeze it later and do it later, but I already started out. An ogive is the graph, an ogive, excuse me, is the graph of a cumulative relative frequency distribution. And it can be done with actually just a cumulative frequency, so that's what I did here. So you just do the counts, or with the percents. And I prefer the percents, but I put both in so that you could see it would be the same. And I want to show you what I did was over here, from 0 to 10, there were 2 or 1%. So from 0 to 10 at 10, I go to 1%, or which would have been 2. From 10 to 20, I'm at 9 people with that score, or 0.045. So this would be 9 people, or maybe 4.5%. And I did that all the way up, and I can connect them. That's a really bad connection. Let's try that one more time. Okay, and this is an ogive. And it's helpful because it can help you find those middle scores. So like over here where we didn't know what proportion scored 45, we can find that now by going to 45 and going up and over. And it looks to be about 20%, okay, or 19%. So that is why an ogive is helpful. I'm going to quickly show you what it would look like on the TI Inspire. So move this over here. So here is the TI Inspire calculator. I've loaded all my data from that chart. Here is just the raw data. Okay, at 10 there were, I'm going to go back to my chart and think about it. At 10 there were 2, at 20 there were 9. It's the raw data, so you can see that it goes up and down. Here is the frequency, the cumulative frequency. So there were 2, and then there were 9. Sorry, over here it was 2, 7, because there were 7 in 10 to 20, which would add up to 9. So we've got the 2, and then plus the 7 is 9, and then plus the next 9 is 18, and it goes all the way up. And if I change this from 0 to 200 people to 0 to 100%, it's the same, and I connect it. And what's cool about this is I could go right here to about 45 and see that it's about 19 or 20%. Okay, so that's an ogive. You will use these a lot, and we'll hit them again in class. You should be able to do them by hand, and it's just basically plotting. The key thing is it'll always go up, it'll never go back down, because you're adding the 2 people to the 7 people to get 9. That's the percent one. Let's do it this way. The 2 people to plus the 7 to get 9, plus another 9 to get 18 total, plus there were 12 in the next one, which gives you 30. And so it should always go up. People sometimes try to do this for an ogive, and it doesn't work. So I'll hide that and hide that. Let's go back to this. Okay. So there's my ogive. So it says, what score separates the lower half of the scores from the upper half of the scores? Well, that's the other direction. Okay, so that would be the 50% mark. Go over and down, and maybe it'd be like 61 or 62. Okay. The pth percentile of a distribution is the value in the distribution such that p% of the observations lie at or below that level. So what is the 30th percentile for this distribution? Well, I go over to 30%, and I just want to know what score is that cutoff. And right here, it looks to be about 55. So 55 is the score. And I really need to put approximately, unless you're using a calculator. Okay, it's just kind of approximate. If I were using the calculator, you could get actual perfectly pretty good data. But about 55%, or excuse me, the score of 55, there are about 30 people that scored 55, less than 55. Okay, 70th percentile, the same thing. Maybe 69, a score, approximate score of 69. That means 70% of the people scored 69 or less. And I should definitely say this is 30% of the people scored 55 or less. They could have scored 55. The median then, we'd meet the middle score. That's also the 50 percentile. Okay, so back to this, that'd be 61. And we could make a box plot. I'm not going to do that for you right now. Well, actually, let me show you. We can just go to our raw data. So our raw frequencies. You know, I'll do it for you in class because I don't want you to have to watch this video forever. But it's actually pretty easy to do on a TI Inspire. Okay, so this is the homework assignment that was assigned on Thursday, or if you're B-Day on Friday, do Monday, Tuesday. Okay, so now let's keep going. When a distribution is skewed, the median and IQR are the best way to describe the center and spread since they are resistant measures. I can't say that enough. However, when a distribution is roughly symmetric, there are alternatives. To describe the center, we can use the mean, or synonymously, the average. Okay, and we're actually going to call this the sample mean if we're taking it from a sample. To find it, simply add up all the observations and divide by the sample size. So x bar means sample mean. This means the sum of x, so add up all the observations and divide by the number of observations. Okay? Notation. In our book, they use the letter y to represent the observations in a data set. So oftentimes they'll use y bar. However, it's much more common to use x bar for the sample mean, so that's what we'll do. Okay, the sample mean is called x bar. Anytime there is a bar over a variable, it indicates the mean. Thus, y bar would indicate the mean of the values of y. It is called a sample mean since it is computed from the observations in a sample. If we had conducted a census and had all the members of the population, we could use mu to denote the population true mean. We use x bar to estimate mu since we almost always are using sample data. The sample size is always denoted n. So if I wanted to know the average GPA for all Hillcrest students, if I was able to get on Skyward and look up all the GPAs and find the average, that would be mu. So mu would be the average of all students' GPA. But that's really hard to do. Instead, I could just poll a few of my classes and take that average, and that would be x bar. So that would be from a sample of students' GPA. Okay. Graphically, the mean of a distribution is located at the balancing point of the distribution. The mean is the value that balances the deviations from the. All right, I paused it so I could make the writing better there in regards to the average GPAs. And then I wanted to draw this. So it said, I said again, that graphically the mean of a distribution is located at the balancing point of the distribution. The mean is the value that balances the deviations from the mean. Bottom line is, if we have our data nice and balanced, it would balance like literally if it was a something in 3D, it would balance right there, okay? If it's skewed, remember this is left skewed, you would have to move the mean over just a little bit to balance it. Otherwise, it would tip over. And similarly, right skewed, you would have to move the mean over a little bit this way. Otherwise, it would tip over. And we'll talk about that in class, and I'll show you an applet, okay? Is the mean a resistant measure of spread? No. Okay, if we put all of your ages together, so student ages in the class, if we took the average, X bar, maybe we'd get 17 or 18. But if we add my age, the average would go up, okay? So let's say I'm not going to tell you how old I am, but maybe the average would be 25 instead. So it moved because we put an outlier in, okay? Another way to measure the spread of a distribution is to estimate the average deviation from the mean. This quality is called the sample standard deviation. And I will show you some stuff about this in class as well. Okay, the standard deviation. Okay, so the basic idea of standard deviation, it's another way to measure variability, which is kind of the range or how spread the data is. Okay, so for example, in the dot plot below, the observations are 2 units from the mean on average. So if you were to add them all up, okay, the mean is going to be 4. And most of the data is within 2 units from the average. Okay, to calculate this, we do a subtraction from the average. So the average is 4. You would just add up all the numbers and then divide by the number of numbers. So that's how you find the average. 1, 2, 2, 3, 5, 6, 6, 7. Add them up. Okay, you'd get your total, and then you divide by 1, 2, 3, 4, 5, 6, 7, 8 numbers. And that would give you 4. And the reason it's mu here is because this is all the data of the whole population. Anyway, we then take each number and subtract it from 4. So 1 minus 4 is negative 3, negative 2, negative 2, negative 1, 1, 2, 2, and 3. Unfortunately, if we were to add these all up, okay, we'll always get 0. So yes, this is a measure of how far away each value is from the average, but to add them up to see the total, it gives you 0. So instead, we're going to square the data. And if we square the data, we will get 9, 4, 4, 1, 1, 4, 4, and 9. Okay? If you take the absolute value, yes, that gets rid of it, but it doesn't show what you want as much, and I'll show you that later too. So finally, we'll add up the squared deviations and then divide them by the number of numbers, or the number of observations, and take the square root. So this is our total right here. It adds up to 36. Divide by the n observations, or 8 observations, and our standard deviation is 2.12, which means on average, these data points are 2.12 units away from 4. And I will definitely give you some real-world examples for this, okay? Unfortunately, when we are trying to estimate the standard deviation from a sample, things get a little more complicated. First, we do not know the value of mu, which is the true average, and we must use x bar as an estimate. Therefore, because the sum of standard deviations from x bar will never be bigger than the sum of the squared deviations from mu, think about that, the quantity, which is our standard deviation formula here, square root of the sum of the differences from the mean squared over n, will underestimate the true standard deviation. This is true because x bar is calculated from the actual data and is the value that minimizes the sum of the squared deviation.